Okay. Hi, guys. I see I have a much bigger group today than I had on Tuesday, which is maybe I'm drunk again, but so it seems to me. I'm sorry to start with such a cheesy joke, but it's geeky and it has some relation to what we're going to talk about today, because we're going to talk a lot about information and how it's stored. And the one thing to remember is that in the end of the day, our computers store data in a binary form. That means it's all ones and zeros, and we won't see much of it in our end of the programming process, but we have to know that this is actually how things are represented. So we're going to start with a presentation. As opposed to the previous lesson on Tuesday, we're going to have more time today because I'm going to be here the whole 4 hours. So I'm going to take it with the presentation and the live samples. We're going to have quite a few live examples today talking, and we're going to get to see a little more of Visual Studio. Did you get Visual Studio, by the way? Did you install it? Did you look at the homework? Yeah, all right, cool. So we're going to look at Visual Studio in greater detail. We're going to see more examples of how to work with C# and Visual Studio as a debugger, how we can follow up what's going on in our program. And since we're going to start using variables and data structures and types, it's going to be quite important for you guys. So let's get started. And as of course, it is not to be even, I mean, it goes without saying that if anyone has any questions or at any point, just ask. We'll clarify things. The important thing here, we're going to have time for working on exercises and all that, but I want to use the majority of the time in really giving a good explanation and getting you to know what I'm talking about. And if anything is not 100% clear, we'll clarify it and we'll talk about it and we'll see it in details. Because in the end, I'm sure that you are all .NET ninjas and just waiting to come out. So we're going to talk about data types and variables. We're going to see the basic data types. This is important because in the end of the day, what we need a computer for is to process data. Our programs or games or any softwares or any applications on your phone or on your computer, the basic idea is to take some data and to do something with it. It could be data that is structured during a computer game that you're playing. It could be a financial data that you're doing with an Excel worksheet. And it could be pretty much anything is in the end of the day data which is processed or stored or saved on your hard disk. It could be a text file, or it could be some calculation that you're doing on the calc. So it is important to get to know what are the basic data types that we are using in our programming language. We're going to see what we call the primitive types. Yeah, we have all these types. We're going to see them in greater details. Some of them are numerical, some of them are textual. I'm pretty sure that some of you know them either from C# or from other languages, other representations of them. And we're going to see a little bit how they are stored in variables and how we can play with those. And then we're going to get a little bit extension of those variables into nullable types. We'll see what exactly that is. So we'll start with the basic types, which are in C#, in the .NET framework, are referred to as primitive data types. Those are the basics that are storing all our information. So as we said, computers always use data in order to process it. Some of it is numbers, some of it is text, which in programming world we'll call strings. And as our tool, as developers, most of them will be stored in what we call variables, which are actually just storage places in our memory and which should hold the data. For example, here we can see a variable called count, and we can see that it's an integer. That means that it's a number, and it will be storing for now the value 5. So far, I hope it's quite clear. Why do we need different data types to begin with? Why do we need to store? Why do we need to know different data types at all? I mean, what is it any difference for us?
It's about the storage they take from the memory.
Yes. Sorry, your name? Ivo. Okay. So Ivo claims it's about the size of the storage that they take in memory, right? Okay, that's part of it. Basically, the memory, as I started with that cheesy geeky joke at the beginning, the memory is always stored as sequences of zeros and one. The computer doesn't know much about anything other than that. So once we are storing data, we need to know where it starts and where it ends. So different data types, we'll see also the reason for that, take different sizes in the memory. So we need to know that at this point starts a number that takes, for example, 16 bits or 64 bits. Bits are the little binary digits that are stored in memory. These are the zeros or the ones. And some of them are gathered. We can say, okay, let's say that 8 of these bits are called 1 byte. This is basic knowledge of how computer memory is working. So once we know how this data is stored, we'll know how much it takes in memory, and our software, our programs need to know how much they are taking so that they can refer to this data and they take it to the right place from start to finish, because otherwise it's all just a blur of zeros and ones. Another thing is that we are getting this information and we need to process it. So our program needs to know if it's dealing with a number, or it's dealing with a character, or it's dealing with a string of text, or it's dealing with a Boolean that says true or false. So all this in the context of our programming, all this in the context of our programs needs to be known to the work environment. So we can see here all kinds of data types, which are, for example, numbers or alphabetical letters, or there could be weekdays, they could be strings. We'll see them all. So as we said, the data types usually have a name, for example, integer that represents numbers. They have a size, so we know exactly how much they store in memory. And they could have a default value that we usually can set or not set. And if we don't set, then they will store the default value that the creators of the .NET framework meant for them to store, unless we specifically put something in them. So we'll start with the most basic ones. It's because of me? No. We'll start with the most basic ones. We'll start with dealing with numbers a little bit. And we'll start with the simple numbers. Those are integer types. That means that those are simple whole numbers that are not with a decimal point in the middle of them. So as we said, they represent whole numbers. They can be signed or unsigned. That's also an interesting aspect. Like I said, the data stored in memory consists of a specific size that we can allocate, for example, to store a number. So if we have 8 bits or 16 bits that store a number, we can say that this number has a certain range. Why is that? Why is... It could be negative and it could be positive. The point is that once you have a limited storage size, this number cannot exceed this size, and it has to be representing only on this specific storage size that it's given. So, for example, if we're talking about natural numbers, let's not go to the zeros and one. If we're talking about natural numbers, and I can say you have a number that is no more than 3 digits big. So that means that you have 3 digits and you can play with them, you can do whatever you want, but you can have, let's say, as many as 999 numbers, from 0 to 999. One thing that can extend that is if we say, okay, these numbers can be signed or unsigned. That means they could be negative and they could be positive numbers. So that way I immediately increased the possibility of numbers by 2. So now I have 999 positive numbers and I have 999 negative numbers. So this thing is just about how we use the storage. Some numbers can be represented as unsigned. That means that we use the whole storage for all the possibilities and we don't count positive numbers. In that case, it could be that we have the whole thing, 999 numbers which are positive, and another set of 999 numbers which are positive. It doesn't make much sense in the real world, but in the storage world of the computer, it does make sense, because these numbers can take the whole space and they can say, okay, this bit now represents whether this number is signed or not, and now this bit doesn't represent that. It actually says it's part of the number, so you have much more space and it's part of your number. So we'll see that types of those integer numbers, those whole numbers, can be signed or unsigned. And another thing is how much space they really take. So we have the default, which is the default integer, which is usually represented just by some numbers. And we have the long integer, which takes more space and can represent more numbers. And they can be also signed and unsigned. Usually when we write numbers in this sense, we'll use the L to specify that this is a long number. This means it takes more space, but it has also more options and it can be bigger. One thing to know is C#, and you'll see it when you're writing your code, is case sensitive. That means that when you write your applications, when you give your function or variable names or your namespaces that we mentioned or objects or whatever, when you are using names, these are case sensitive. If they are with lowercase letters, they have to be put with lowercase letters. With a very few exceptions. When we're talking about these numbers and these signs like this that says this is now a long number, these are unsensitive, the insensitive cases. So you can put a lowercase or uppercase. The problem is that if you put a lowercase L, it can appear to another programmer like you put number 1. So it's part of a number. And I think that if you try to build your application and put a lowercase L, it will warn you that you might be confusing somebody else. So here are the basic integer types. What we can see here is for each one of those types, we have the short byte, which is called S byte. We have the normal byte, and we have the short integer and the unsigned short integer. We have the normal int, which is a 32-bit integer, which is also sometimes called int32, and that's the most commonly one used in these cases. And we have the unsigned int. And we can see that in the brackets we can see how much space in bits these things we can see how many bits each one takes, and in the brackets we can see the range of these numbers. So you can see, for example, the short byte, which is assigned 8-bit, it takes from -128 to 127. Why is it not 128? 0 is also a number, of course. It has to be represented as one of the numbers. So you can see that we have a range of 256 numbers, but they are split between the signed and the unsigned. Once we remove the signed or unsigned and we go to the normal byte, then they are all moved to the unsigned. They're all positive numbers. So we have the same range of 256 numbers, but they are from 0 to 255. And the same goes for the short and the unsigned short and the int and the unsigned int. You can see that it doubles the range, but it gives you less numerical places to play around, and that really depends on your needs. If we are talking about, for example, ages of people, there is no use of putting spaces in unsigned because nobody is in age -1 except Chuck Norris. These are again two more types which contain numbers, integer numbers. These are the long and the unsigned long, and you can see they're pretty big. On 64 bits you can do 18 trillion, zillion, gazillion numbers, or whatever this one is called. So far, questions? We're going to see a small demo with integer types. Let me reopen Visual Studio from scratch so we can see what's happening. What I have here is the solution, which you can download from the Academy website. You can download all the PowerPoint presentations that are presented in class, and you can also download the demo materials. So the demo material comes in a zip file, and when you extract it, you get a solution with all the files that you need in order to run those demos yourself. So when I open this SLN file, that as we could see is a solution file for Visual Studio, and we mentioned it on the previous lesson. Is this clear enough? This thing is all the time flickering. I don't know why. But since I don't know why, I don't know how to fix it. So we can see in Visual Studio that we have now the solution open. And here on the side, let me actually open a more standard window here called Solution Explorer that I mentioned. Actually, this solution today contains many projects, not just one. And each one of these projects is a console application in itself. So when I build it, if I build the solution, I'll see that each one of these projects has a binary folder with a created executable which is completely separate from the others. So you can have in your project in your solution many projects, and they can run separately and they can coexist, just so you know. So we're going to start with the integer types. What we can see here, maybe I'll increase it. Nope, not this, not this. Yeah. So we can see here our main application again. Just to remind you, we are wrapping it by default. It has some class. This application doesn't have a namespace, this file. And we have our class, and we have our main section, our main function, just as we could see at the previous time. What we can see here is simple definitions of variables. We'll talk more about variables in the next part of this lecture, but it's pretty easy. We have, first of all, the type of the variable, then the name of the variable, and then the value which is set to it initially. This is called initializing it. So we can see we are putting it into centuries, which is actually a small byte. We don't need much for small numbers. We have the unsigned short, which takes pretty much the same size, but it's unsigned. We have the days, which we already put an unsigned integer, which is 32 bits. And we have the long. For very big numbers, we can put here a very large number with many digits. This next line is also interesting. What we have here is the console Writeline statement that we saw in the previous time. And as you can or cannot remember, it writes a line into your console. Yeah, that's cool. One thing to know about this syntax here, as you could see on the Hello C# application in the previous lesson, we're just putting here a string. Oh, don't move it. We're putting here inside the brackets a string, and you can see that the brackets start and end on the next line, which is okay. But we have here a number of other variables put into this section between the opening and the closing of the brackets. And inside the string we have what we call placeholders, which are numbered from 0 to 3, which are put in those squiggly brackets. And those actually correspond to the variables that we put here. So the first will be the centuries, and it will just print out the value of this variable right in this space instead of this placeholder. Then here inside the string we'll have the years placed in here. They are replaced at runtime. If we run it, nothing much will happen. Yeah, will open and close. In order to stop it from running, by the way, what we can do is we can read something from the user. That means that we are waiting for user input. That's one of the options. You can just hold your program from closing immediately. So if instead of writing, I'm trying to read something, that means the console will now wait for my input, and that means the window won't close so quickly. So if we run it again, we'll see the console, and we'll see the strings with its variables printed out. That's what it does. And since now it's trying to read something, whenever I click a key, it's trying to read one keystroke. When I hit a key, it will close. One important aspect of Visual Studio that you're going to have to get to know quite well is the whole debugging, which I wanted actually to demonstrate in the previous lesson, but didn't have all the time for. So we're going to see, I'm just going to make a quick demo of how this is done. We have the debug menu here, and we can just call start debugging, or with F5 we can just hit F5 and it will start running the application, which basically will do exactly what we did until now. In order to stop your execution at some point, we can just place the cursor at a certain line that we want to stop in, and can hit F9. Uh-oh. Okay, the recording software takes the F9 from me, so I'll just click beside the line, and what we get here is a red sign of a breakpoint. That means that now when I run my application with debug mode, I'm stopping at a certain row, and I can see exactly what's happening here. So if I have variables like here, I can place my cursor over them and I'll see their values. This will work also for more complex variables like classes that you'll be handling later. There are also all the debug windows which are available. So under the debug menu now that I'm running, I have a section called Windows, which is much more extended than when I was not running, and we can see all kinds of windows that are helpful. One of them is the Watch window that I can see down here, that I can just take a variable and drag into it, and while my application is executing, I can see what's happening to this variable. I can see if it's growing or going zero, and that's actually the essence of debugging, to see what's going on inside your execution. So we can go on to the next line, and I'll see that right now I have a window open of a console, but nothing has happened in it. But if I'll continue to the next line after this execution of console Writeline, then I'll see that in my window I already have the text printed out. To stop the debugger, you can always click Control F5, Shift F5, or up here there is a toolbar with control buttons that can stop the execution for you. So that's pretty useful. Any questions about integer types so far? Yeah?
Does Express have that watch?
Should have. I personally haven't used Express. I've only used... Do you have the debug menu?
Yeah.
But you don't have many windows in this option.
I have Windows, I don't have mention.
Okay, that's because you're not in debugging. You're not in runtime. If you start debugging and stop on a breakpoint, then see the menu, it should appear. One more thing here about this whole environment. By the way, Visual Studio is quite open to all kinds of extensions and plugins, and in Telerik there are teams which are developing Visual Studio extensions as well. For example, this one which is called Just Code, which is a Telerik product which plugs into Visual Studio. And all these windows that you see around can be collapsed, and they can be extended, and they can be dragged. So the whole structure here is pretty much changing to your will. If I want to take this properties window and place it down here, I can do it. I can make it collapse or not. And now it will collapse, it will stay, or it will collapse down, or maybe not. Well, something like that. Just so that you know that this whole environment is dynamic. It's not like the old compilers that are structured in a window, and what you have here you can add, open all kinds of windows, stick them to any corner that you want, and they can collapse or open at your will. Now this fun starts. The same space that we have for storing integers is used for storing floating points. What are floating points? They represent real numbers. This is, by the way, the reason I'm wearing this shirt today. This is it. It's a geeky joke again. Those of you who studied a little bit math will know it. Someone's trying to get in. The floating point types that we're going to see are actually for storage of real numbers, those with a decimal point in them. So we have to be a little smart to store in the same kind of zeros and ones to know how to store a decimal floating point number. So there are all kinds of tricks for that, and those tricks also cause all kinds of problems. But just to know that once we are storing a decimal number with a decimal point in it, we have to know what the number is, what are the digits, and where is the point placed. And according to the placement of the point, we can have all kinds of sizes for the real part and for the integer part of the number, and this causes a lot of other problems. For example, they can behave abnormally in some calculations, and we'll see something that looks very trivial, but it doesn't work like you would expect. So these are the main two types that are used in floating point types. One of them is called float, and the other is called double, because it's double the size, double the precision. Now that we have a floating point with a decimal point in it, we have a floating point number, we're talking about how much we can store, but also about the precision. That means how many places from the dot we can have. So in order to specify a float, we would usually put f after, and again, this f is one of the few rare cases where it's not case sensitive when you're typing it, and this d, which represents the double. And we can see the ranges of these numbers are pretty big, as you could expect from a 32 and 64 bits numbers. So here's an example of what happens when these floating points don't really behave as you could really want them to. We have here a declaration of a float, which is representing pi, or I think it's supposed to be said p. But where I come from, we always call it pi. So since we are declaring here a float, by the way, we have to explicitly place the f here at the end, so we know that this number represents a float number. And we have the double, which is also placed with the same numbers in it. We are just feeding those two variables with the same decimal point number, and we are printing them out. We'll see this in the live sample too. But what we can see is that the first number is much shorter. Again, because we're dealing with float and then we're dealing with a double precision, we have much more space to store, and this thing gets cut after the sixth digit after the dot. Here's another example of what's happening, and that's a little more strange. We have here two double. Can you see? Can you see it? Yeah. Okay. So we have two doubles. One of is A and the other is B, and we're just placing very normal numbers. One of them is we're placing 1, and on the other we're placing 0.33. And we have another one which is called sum, and we put into it 1.33. And we would expect that if we summarize those two numbers, we'll get 1.33. But in reality, we get something which is close to 1.33. These float numbers, because of the way they are represented in memory, and if you want to learn more about that, there are many articles that talk about it, including some in Wikipedia, which are quite lightweight and easy. But the way that they are stored in memory makes them sometimes behave as if they are not actually the number, but they are a close approximation of the number that you're putting in. That's because they are stored as fractions, and they are trying to get an approximate value to what they're supposed to store. There is a way around this. There is a better way to store a floating point if you need exact numbers to be stored and not approximations. And that's the decimal number. Decimal number is big, 128 bits. It has a precision of 29 digits, and as you can see, it goes quite big. It is stored as decimal on the base of 10, if this means something to you, not as a decimal on base of 2. It's not approximate, and it stores large values, and it can be very, if you need accuracy with your floating point numbers, then this is the one to use. Since it's so big and it stores so many numbers per each number, it's also not very performant. It's slower, but if you need accuracy, that's the pain. The M is the postfix, the suffix that denotes that we're dealing with decimal numbers. Questions so far? So I'll go to the second project in the solution, which is called floating point type, and there is a CS file here. Again, this is a console application, and we'll see here first of all those two demos that we saw in the presentation. The first one that puts the floating numbers of P and prints them out, and we'll see that one of them takes much less space and that therefore much less accurate. Then we'll see the abnormality here. We'll see exactly what happens with those variables in their summarizing. And then we'll see the same example using decimals, and we'll see the decimal can just do pretty much anything you ask it from. And that makes much more sense because computers are built to serve. So we'll stop. We'll just make another debugging session here. I'll just put a breakpoint here, and we'll run it. And we'll clear the watch window. Let's take these two values here. And as we can see, even though they were both fed with the same data, one of them is much smaller. And it was printed out, as you could see. Now the doubles with the floating, which we're feeding with floats, which could be problematic if you need accuracy. So let's look at what happens with A, B, and sum. So it seems like we have 1, but look what happens with a 0.33. It's immediately distorted. It's close to. So don't count on that. And when we're adding it, actually, we're not really getting the sum of these two figures because the numbers after the point are different even after we summarize it. We have another variable here, which is a Boolean variable, which we'll see later on. We're just trying to get to understand whether a plus b equals the sum. And obviously, this variable is false right now. This means that this condition here is not true. So if we put here 1 and 0.33 and sum them up, we don't get 1.33. So here is the output of this. Float calculation, a plus b is equal something. The sum, which we put explicitly 1.33, is equal something else. And it's a big celebration. Now we look at the decimals, see what happens there. The decimal one is actually showing, let's see it from close up. So the decimal actually shows that it contains the integer number 1. That means there's no floating point. It's not used here. It's not necessary. The other decimal shows exactly 0.33, and the sum shows exactly 1.33. And of course, if we're trying to find out whether these are equal or not, on the next line we'll see that this is true, and the console will also write it for us. We'll see the numbers much more neat and nice, and they are accurate. So depending on your needs, if we're talking about ages, use integers. If you need small numbers, use shorts. If you need long numbers, use longs. If you need high accuracy, use decimals. And if you're building a math science project and you need approximate accuracy, you can use floating points like float or double. Questions about this demo? About what's going on?
Is it obligatory to put the suffix f, and what happens
if you want to use floating points, if you want to use a float number the size of a float, not a double accuracy, you have to put f. If you don't place those, I think the default is double. So no, if you are creating a decimal, you have to specify this. I'm not sure. You see, if I don't specify f, then what I'm putting in is a double. If I put f, that means that this is now put into a float, and that's the size it will be taking. So we're not using the double accuracy because we don't need it here because this is a relatively small number. But if we need higher accuracy with more numbers, more digits, then we could use the whole double. But if you're using floats or decimals, you have to specify that this is a float and this is a decimal. Of course, for integers, all kinds of integers, you don't need this. But in the end of the day, like I spoke in the beginning, your computer needs to understand the size of the data that we're talking about and the accuracy of it and what type it is so we can play with it. Like here, we're talking about numbers, and our .NET framework that runs the application understands that these are numbers, and this is actually summarizing them. If those were strings and I would put this plus sign between them, it would act completely different. And we'll see that.
What is the situation if we are using double in the first case?
I think it would be
It will be true or false?
I think it would be false, but let's try. If God wanted us to know everything, it wouldn't give us a debugger. So let's see. Okay, so I'm stopping here. No, it is accurate. Double accuracy is better. It's sufficient for this. I think that for larger numbers with more digits, we would get probably
False.
we would get false.
And if you repeat the same as it was with the suffixes you will see that the digits were with the exact number of zeros after the point, and
Mhm.
then was the garbage.
Mhm.
So it means that makes them limited to all the zeros that we meant to
Mhm.
be interesting to us.
Yeah. When they are actually coming after the floating point,
Yeah.
the whole part of the number
Then what
is
about
okay.
if we declare them as float numbers and
I think it will be the same effect. If we change this from being double to being float, I think we'll have exactly the same. We can't, of course, put a double here.
No.
We have to feed it with a float number because that's it. Huh. Actually, it's good.
So it's just mixing with when we declare double, but takes
Yeah.
less accuracy with explicit typing.
Mm. Yeah, so it seems, even though I'm pretty sure that there are cases where this thing will not work as good, because those floats are sometimes not acting as they are expected. There are abnormalities which are related directly to the floats. But good point. Any more experiments or questions?
With doubles, it's true, by the way.
Hmm?
With doubles, it's
Yes,
true.
we've seen it. Okay, simpler types. Boolean is known. This is also for those of you who've been working with any kind of C++ or other languages. Boolean is also a very common data type. It's simple. It can only contain true or false. And that's about it. You'll see a lot of logical expressions. You'll have to use all kinds of logical expressions and conditions in your programs. So understanding when a certain condition is true and when it's false is very useful, and these booleans are used everywhere. If we don't specify any initialization for a boolean, it will be obviously false. So here's an example, which is pretty much close to the example that we saw before with the sum. We have two numbers, 1 and 2, which are ints. And we're building here an expression, a Boolean expression that will tell us whether A is greater than B. And in this case, it would be false. One thing to know that when you are comparing something, we're using the notation of double equal sign here. For example, if I want to check whether A is equal to 1, we will have to put this double sign. And if you don't, this will actually assign 1 to A, and this will not have a Boolean meaning. So mind you, when you're putting a one equal sign and when you're putting two equal signs, it's a common beginner's mistake.
What size does the Boolean type take? Is it 1 bit or is...
I think so, but I think so, but you cannot. In C++, for example, the types are more intertwined. You can have Boolean, which is actually, I think that they could be casted into zeros and ones, but here the value has to be explicitly true or false. Okay. Another sample. This is again the same example as we saw in the presentation. So we can see the variables are initialized, and this Boolean variable contains already false. And since we're here, we're checking whether A is equal to 1. we'll see that this condition is true, and this variable, which is called equal A1, is also set to true. Quite as simple. Once we run it, we get our output as we expect. By the way, you could see here that there are two statements of console write line. So on each one of them, we're writing a separate line to that console. Characters. Characters contain all kinds of textual symbols. By default, the .NET framework characters are Unicode characters, unlike older development environments and languages where a character would be what is called ASCII character, which is limited to 8 bits, I think, which I think is 256 symbols. This has been long time since this has been extended to a standard called Unicode, and so it has at least a double number of bits. We can see here it says also 16 bits of memory. That means that we have much more options, and this should cover pretty much all the textual symbol characters of languages used by humans.
Even the Chinese letters. I think for Chinese letters they're using 3 bytes.
It could be. It could be. I'm not sure. I think I've heard about that. Never checked that thing, but it could be that they use a larger format. Of course, in the underlying memory storage of characters, they are stored as numbers. Each character symbol has a corresponding number that identifies it. For example, I think 65 is the letter A. That's the only one that I could remember from the old format. So we could see that we have here 3 variables storing characters. Characters are they have to be put in a single quote to store them. So we put our character to store in a single quote here. And of course we can see that here we have a lowercase a and here we have uppercase a, and we'll see that those are completely different. They're completely different codes. And another thing we can see here is something called casting that you'll run into quite a lot. And that means when we have a variable of a certain type and we want to throw it into a different type and make the application think that it's a different type, we can put the other type in brackets in front of the variable. That again, as I mentioned, we need our software to understand our data types so that it knows how to handle them. But once we are casting like this, we'll be taking it as a number. So if this letter is represented by a number actually in memory, this will bring us this number casted into an integer, so we'll see what code it is. So that's also important to note. Let's see it running. Let's put a breakpoint just before our main function finishes. We don't need the watch. So we have here 4 different variables. The first one is the small lowercase letter a, and we're printing on the first placeholder the letter itself. And here we're putting the integer value of it by casting it into an integer. What happens next is that we take our same variable that we stored here and we just assign it different values. So we're putting the letter lowercase b here, and we can see that they come on sequential numbers. So A is 97 and B is 98, and the uppercase A is 65, and here we have a Unicode character, which is not part of the ABC. I mean, it is, but it's not part of the regular ABC symbols, so it's much higher in its value to 249. All right? All right, what happens when we have many characters? We put them in a string. This is, by the way, the first verse of Genesis, written in Hebrew here. In the beginning, God created the heaven and the earth. That's what it says. So string types represent a sequence of characters. In C#, they are declared by the word string. In C++, it gets a little more complicated than that. We'll see about the null value as we go on, but it's important to know that an empty string is null. That means that it has no value at all. And the string has to be put in double quotes, as we can see here. And what happens when we want to put the double quotes inside a string, we'll see as well. We could take two strings and put them one after another and make a bigger string if we use the plus operator, just like we did with numbers. That will take them and concatenate them into a bigger string. So here's an example of such concatenation. We have first name and last name strings, and we are printing on the first console Writeline the first name. And here we are declaring another variable called full name, first name, and last name, and we are concatenating them. But also note that we are concatenating another string with a space character in it, because otherwise they'll just be going without any break. And printing the full name string here. So let's see some strings. Here's the demo again, the same one. And a breakpoint just before we close. We can see the variables, first name and last name. And we're printing here the first name, so it will be hello Ivan. And the full name, once we are concatenating both strings with a space, it will give us one longer string. One bit of information which you may just want to know as a trivia. Once you concatenate strings like this and you put them in a plus sign between them, you're actually creating a new string from scratch. And that's a process that just every time you concatenate another part to your string, you're just recreating the whole string again. That's not very performant, but that's something to know. There are ways around it. There's something called a string builder that does it more effectively, but just so that you know, in terms of program performance. Questions about strings so far? Great. All right. That's the time, by the way. I know that you guys are after a working day, same as me. If you feel like taking a break for a coffee or something, we could take a short break so you could refresh. You okay with that? All right. So let's take a 10-minute actually, because that's the default. Okay, everybody's here, I hope. Whoever isn't. Okay. Originally, I wanted to give this break in the beginning of the lesson so you could just have some coffee and this, but since we are pretty much on the halfway of the presentation, I thought it would be good to cut it in half, and then it will be easier, and then we'll have this exercise segment, so it will be also easier. So we'll continue going through the basic types of the language, and this one is pretty less intuitive. Since we were mentioning that C# is a very object-oriented language, all of its data instances, all the data that we're using, can be defined as object. We have classes and objects, and you'll see a lot of those in further parts of this course. So object type is the basic type of all the objects which are used in the language. So we can define it with the object, and we can create objects which are, what is this? We can create objects in our program which hold any kind of information, and this is also something which can be changed. I mean, if we said that, we mentioned that once we are storing data in a variable, we need to know the type so that we can know how much it can hold and how the program should handle it. So object types are a little bit more open to that, because they can represent pretty much whatever we want. So here's an example. What we have here is an object, variable of type object, which contains the number 5. And then we can put into it a string with the word 5. And even though these are two different data types that we're dealing with, we can store them both in one variable. Usually this would not be possible without some kind of conversion. So let's see it live. Breakpoint, and running. Why am I not getting? That's why. Okay, so this is our code from a closer look. Let's actually put a break again. Let's run it again. And we'll see that on the first part, the container here contains the number 5. And after this line, it contains a string. There is also a difference in how objects are managed. You'll see differences between types, which are known as reference type, and those are known as value types. Simple types like integers are usually referred to as value types. That means they are stored in a certain part of the memory, which is usually called the stack, and they are static. You can place data in them, they store them. Once your function or your code block exits, they are no longer there. They are taken out of this stack area. More complex types like objects are stored in a different type of memory, which is called a heap. And the whole .NET framework manages the data which is stored there. So if we put a data of type object here, and even though we are storing a simple number here, it will be stored in the heap and it will be managed. The whole memory consumption will be managed by the .NET framework for us. Yep.
I have seen sometimes declaring variables as var type.
Yes.
Is it still an object?
Yes. I'm still debugging. Basically, var types can be anything. Here I'm declaring a string variable, but instead of using the string keyword, I can use this var keyword. Or I can declare a float and put it into a var. Actually, I can create any kind of data type, and I can create my own classes, and I can store them in variables called var. And this is an open thing. Actually, once the application is being compiled and built so that you can run it, it's interpreted, this type is interpreted as what it really is. So this one will be converted to a string, and this one will be converted to a float. They are still hard-coded types. The only difference here is that during the time where I write the program, I can put the word var and play with it. I cannot change it because it's still hard-coded once it's assigned. No, I don't want to fix this. But personally, I'm not a big fan of the var variable. I think that the fact that C# is a strong type language, and once you see a variable, you need to know what it is and declare it. I usually declare variables with their real data type name. But many people seem to like var because it's easy.
When it's compiled, does the variable go to the stack or in the heap?
Depends on the data type.
Okay.
This is a real. This is just, as far as I know, it replaces the type name. So it could be int, it could be a class name, it could be anything else. But once the program is compiled, it is converted to an actual type. So this makes easier writing, but harder reading. And I'm not a big fan of var. But it's an option that you should know of. More? Okay, so let's talk about variables. We've talked about how data is stored. We've seen the data types. Actually, we've seen only the primitive data types, which are storing numbers and strings and things like that. We've also seen variables in our application. That means that once we have some data, we need to store it somewhere. So we've seen already declarations of variables, how they are produced. We have the name of the type, for in this case it's an integer. We have the name of the variable, in this case counter, and we have an initial value which is optional. If we don't put an initial value, the variable will get a default value, which in this case would be 0. If it's a Boolean, it would be false. If it's a string, it would be null. So this is the formula of how to declare a variable. You need, of course, to finish your lines with semicolons. Give them names. The names should contain letters, digits, or underscores, and they cannot start with a digit. They have to start with a letter or underscore. One more thing which we already mentioned is that they have to be, they are case sensitive, so if you declare a variable with a lowercase a, it will always be a lowercase a in this case. And of course, a variable cannot be a C# keyword. For example, the word true or the word new, which are used in the language itself, cannot be variable names. As good practice, also mentioned in the previous lesson, variables should have names that are understandable. Don't name your variable I, J, X, Y unless you have a good reason to do that. Many times if you're making a loop, which you will, those counters are okay to be, let's say, I and J. But usually if you are creating variables, you better give them descriptive names so that the person who debugs your program doesn't find you and kill you. So, as a recommendation. And as we said, they are case sensitive, so once you declare them in a certain way, that's the way they're going to be. So here are some examples of variables. Notice the first line, int, which declares a variable called new. And notice the first line down here, which declares a variable called new. And of course, these are different. And new is a word which is used in the C# language to define new objects. So it cannot be used as a variable. This would be an error. This, however, will not be an error. This is a variable with a name which is different than the reserved keyword. Also, we have here a 2-pack, which starts with an underscore, and we have a 2-pack which doesn't start with an underscore. This one is illegal because a variable cannot start with a digit. You could, if you want, use Unicode characters in your variables. It's not highly recommended. And part of the reason that this course is transferred in English is that English is the global language of the computer world, and it's better to use it when you're declaring variables in your program. As we said, don't name them n unless you could name them something more descriptive like number of clients. This is also a very common notation. Once you have a variable that comprises of many words, you could put the first letter as lowercase, and on every new word put an uppercase letter so that it will be more understandable. Or you could use underscores. That's up to you, or up to the convention of the project that you're working on. It says here that this is an over-descriptive identifier. That means it might be too long for people to read. But personally, I believe there is no such thing. I think that your variables must be well descriptive, and if you need to give it a long name, give it a long name so it will be more understandable what it is and what it's for. Okay, assigning values to variables, as we saw in the examples, also just using the equal operator. So once you have a variable and you have a value to put to it, it could be a value of another variable, it could be a literal value that we'll see further on in the presentation. Just place it, and that's pretty simple. Here are some examples of assigning variables. We have the first value and the second value and the third value, and the first value is assigned the number 5. The second value is not assigned a value by default, so it would take 0, and the third value is not assigned, so it will also take 0. And here we are assigning first value into the second value, so that means we're taking the 5 here and we're placing it into the second variable. And another interesting sample here is that we can actually chain up more than one assignment. In this case, we're taking the value 3 and we're assigning it to the first value, and then we're taking it and we're assigning it to the third value. It is possible, although not very common syntax, and it could be confusing. And usually when you're assigning something into something, make sure that you have one statement assigning, and that's it. It will be much simpler. Initialization, as we mentioned, once we place a value in a variable, we could assign it in the declaration itself. So we're assigning an int, we can immediately put it in the 5. Once we're using a variable, it is better to have its value assigned. I mean, if you're using variables in your applications, make sure that they're assigned values, because then it could be, even though if you're taking a Boolean and you're not assigning anything to it, it will be the default false. But if you are not explicitly assigning anything to it, it could be also a term of bad practice. It's usually better, whenever you have a variable, it should be initialized with some value, or assigned a value, or transferred a value. We'll see also another way of creating a variable with a new keyword. That's actually something that you'll be using much more when you'll use your own classes. But it is possible to create variables, for example, of type int, using the new keyword. We'll see a lot of literal expressions like numbers or strings. We'll see a lot of that later. So again, these are assignment variables. We've seen them. This float, which we are assigning 1.74 in the precision of a float. Here we have two variables. One of them is greeting, which we are assigning a literal variable of a string, and here we're creating a second variable, and we're assigning the value of the first variable into the second one. The more interesting sample is this one, which creates an integer, but instead of taking a literal value and putting into it, we are assigning it with a new keyword here. This is how we initialize different data types in C#, and you'll see a lot of that when you build your own classes. It's very unlikely to see this expression when you're using integers, but it is possible. So integer is just a class like other classes in the language. Let's see it live. So again, these are the same samples. Let's put a breakpoint and let it run. So we're starting here with 3 variables. Only the first one has an explicit declarative assignment initialization. So it is 5, and the other 2 are zeros. And assigning the 5 into the second variable after this line is executed, we can see that this one is also 5. This is a 3-way assignment, which is legal, but not very...
Bad practice.
Bad practice. But it works. And it's important to know that when assigning, we're usually taking from right to left. So the value that we're assigning starts from the left, and then assigned to this, and then assigned here. Initializing an integer with a new instance. It works, but again, not useful so much when using integers. Floats, as we've seen already in the previous demos, assigning a float. And the strings assigned in one into another. Just a small close-up on this console Writeline. We can see again that we have here a string with placeholders, and each of them, of these 7 placeholders, numbers from 0 to 6, are going to take those values and print them out. Between those, there are new line characters which are going to break into new lines. So that means that the first value is going to be in a separate line, and then we're going to break line, and then the second one comes, We're going to break the line again, and the third one comes. So we can see that if we run this line, we can see the output here, and we'll see that each one of those values is in a separate line. So just so you know that if you are printing into the console, and actually if you're building strings, you can put the new line character in them and you'll get a multi-line string. So far so good? Great. Literals. It's hard to explain what literals are because they are the most trivial of all. Literals are actual values that we can use into our variables. For example, we can have actual numbers and we can put them into a variable of type int or float. We could have an actual string with quotes, so that would be a literal representation of a string. And there is also the word null, which is used to represent the nothing. Again, in C++, null is equivalent to 0, is equivalent to a 0 pointer. In C#, null is the absolute nothing, and it can be assigned into various value types and various more complex types. But just so that you know that if you run into null, it is actually the absolute nothing in C#. So for Booleans, we have two literal options. One of them is true, and the other one is false. Those are reserved words in the language. If we are putting any numbers, we can put just the number itself. For using in all kinds of integer variables, we can put a sign. If it is an assigned kind of integer, we can put a plus or a minus to make sure that it is signed correctly. And also, if we're putting numbers, we'll see that we can actually we can assign a hexadecimal number to them. If we want to put an hexadecimal representation of a number, we have to start it with a prefix of 0x, and which is again the x here is case insensitive, like with the other number options. So if we put 0x8f1, this is a hexadecimal number, which I am not sure which real number it represents, but we can easily check that. It is equivalent to hexadecimal number in this format would be equivalent to an integer number of some. We can see it in the calculator application. Yeah. We could use suffixes that we've already seen. We can use the F for floats. We'll use the L for long. We'll use the U if we have an unsigned number. We can use the M if we have a decimal. So these are also this is just actually showing how you can construct integer number literals that you can assign. Here's an example. We have here a hexadecimal number which is assigned to a minus hexadecimal 10, which is 16, I think, or yeah, should be. And we have another assignment of the 16, right? Yeah, because hexadecimal is 16, and once we're taking the second digit, it becomes 16. We have an assignment of an integer minus 16 here, which is on the basis of 10. We have an unsigned int, which we're assigning to 234, and we can also specify it with the U here. We have a long int that we're specifying with the L, and as I mentioned before, L, since these are case-insensitive notations, can be put with a lowercase l, but if you're putting a lowercase l, you may confuse with an 1. You won't confuse the compiler, but you'll confuse other users who read your code. The real literals, those are with floating points, We've seen the F and the D and the M. One more notation possible to remember is that we can also make an exponential notation if you have very large numbers. That can save some typing and be more understandable. And if we're not noting anything on floating point numbers, they are by default doubles. On the other hand, as we've seen, if we don't put F on a number and we're trying to assign it to a float, we'll have an error. Because if we are assigning to a float, we have to specifically put the F in order to notate that we're using a float. Characters. As we've seen, using characters as literals to assign to a character, we have to place those inside a single quote, and we have to put just one character inside. It could be a special character. That means it could be a line break character. It could be a null character, which ends usually with strings. In that case, we'll have to put the right notation. So, for example, a character could be character could be one of these special characters. For example, since we are putting our character in a single quote, if we want the character to be a single quote, we'd have to put it in an escape sequence. That means all these options which are starting with a backslash and then put the character after those. So we could put the single quote, so we have to first put backslash and then single quote, and it would be interpreted as a single character. But if you want to put if you want to put the backslash itself, you'll have to put two backslashes. So these are the common escape sequences. We've seen the /n, which is actually a single character which denotes new line. And if you want to use a character of a double quote, which would usually be used in a string, we'll have to escape it with a backslash double quote. Another option is to put the value of the Unicode symbol, if you know what it is, if you know that it's number 65, to create a uppercase A, you can put /u and then the code of the character you're trying to produce, if you don't know how to type it. So again, here are some examples. We have a character here which is placed with an ordinary symbol of the letter A, or we can put the symbol of a special Unicode character which is denoted by the hexadecimal format 6F. Oh, here's a traditional Chinese character which is denoted by the Unicode 0449. Here's a single quote which is actually denoted by a backslash single quote. This is a backslash which we have to put as two backslashes. This is a new line symbol. /t is a tab. And this would produce an error because once we're dealing with a character, we have to put only a single quote. And if we're putting double quote, that would denote a string. As for strings, there are actually two options for creating a string. Here it's referred to as actually there are two options for a string. The one that we've seen so far is the one which is put in double quotes, and there's an option to prefix it with this @ symbol, which makes it easier. We'll see a demo of what actually benefits we can have with this. These are called verbatim strings. I hope I can type right here. That's the correct term of using this symbol. Once you put this symbol in front of a string, you can put anything you want inside the string except the double quote that closes the string. So if you have, you can use it with backslashes, you can use it with new lines, you can use it with question?
No.
Oh, all right. here's a sample. So on the top, we can see a string that contains double quotes in it. So in order to use double quotes, we have to escape those double quotes with backslashes. So here we have a double quote and a sentence and another double quote. Or for example, we have a path of files, so we use backslashes to denote C/WinNT/, but each slash has to be put with a double slash so that it will be produced correctly. But if we use verbatim strings, here it's called quoted strings, I think I'm not sure this is the right term. For example, look at the path here. Once we're opening the string and closing it here, we can put pretty much anything, and we're using normal slashes, normal backslashes. We don't need to double them. And the quotation, instead of using the backslash quote, we can use just a set of 2 double quotes that will be translated as a single double quote. Or here we have a string with a new line in it, and actually it starts here and ends here, and it's still valid. If we're not using this at prefix, this will not work. So let's see some strings. Again, we have here a sample of those two types of strings. First ones are normal strings, and these are verbatim strings, which are using the notation starting with the at. We can see that here we're much more free, except when we want to put a double quote, we still have to put 2 signs. So we have to put 2 double quotes instead of backslash double quote. And running it give us the desired effect. You could see that the output is actually the same for both options. It's only a notation for us. All right, nullable types. Types which are primitive types, such as numbers, usually would not contain the null value in them. That means that once we're specifying an integer, no matter what value you put into it, it will always be interpreted as an integer. If this space contains only zeros, that means it contains nothing. It will be interpreted as an integer of value 0. But sometimes this comes useful in all kinds of programming scenarios. We want our variables to contain also an option of not having a value at all. That means they are not initialized. That means that this is a special case where we want to make sure that the user has input something. So if we are planning on, for example, on an integer, and we want the user to input some kind of value into this integer, we want to know whether this variable contains a value or not. So we could extend those primitive types to be what is called nullable types. And that means that it could be an int, but it could also contain the null value. That means that it has absolutely no value put into it at all. So in order to create a variable of nullable type of integer, we have to add the question mark after the declaration of the type. So integer with a question mark is a nullable integer, and the same with a double. So we have our regular range of data as we've seen for integers or floats or doubles or strings, but these are nullables, so that means that they can also be assigned a null value. That means that they have absolutely no value. So here's an example. We are declaring a new integer, which is called some integer, but we are assigning the null value to it.
I have a question. If we are not assigning the null value, are we going to get 0 or?
I think you'll get null in this case. Since it's nullable, we can try it. So in this case, we can see. I don't know if there is a sample, but if there isn't, we'll produce one. So we'll see that this integer at the beginning contains the value null, and only then it's assigned an actual integer value, and then it's printing the value of 5. Same with the double. We have here a double, which is a nullable double, and we can see that only here it's assigned, and then let me see. Let's create a demo. Okay, I'm going to start a new project, and it's going to be, again, console application. We call it Nullable Types Demo. Here's my basic program method, and we're going to declare an integer which is nullable. We'll see what happens to it when nothing is assigned. Notice another thing here, that the nullable types have another additional property which the regular types don't have, and that is we can actually check whether this nullable type has a value or not, and that's a Boolean component of this special type that can show you whether or not this one contains any valid value or it is null. And also you can get to the actual value if you type .value, but this will be valid only if your integer has a value. So let's type out the value of our nullable int, like this. Without assigning anything to it. And we can see the value of this has value component. Then we assign some kind of value to it, and we'll repeat the write line. So when we run it, we'll have an error. Okay, so this will not run at all, to your question. If you're not assigning anything to a nullable type, you'll get an error of using an unassigned variable at all. This will not run. So we'll have to explicitly set it. And now we can see the two outputs. It has no value. It is set to null. It will print absolutely nothing. And the has value is set to false. Once we assign something to it, we can see the value, and the has value is set to true. Yeah.
Can we compare nullable types to not nullable types? For example, would it be correct if we write nullable int greater than 0 or smaller than 0?
Yes, I think that should work. Let's see it then. Let's see it. So we're assigning a non-nullable. And we'll put here a Boolean expression. And we'll print the actual value of the Boolean expression here. So the comparison works, as you can see, that our Boolean expression is true. That means that these two are comparable to each other, and they are actually declared as, they are identified as equal to each other, even though they are slightly different in their implementation.
Is null smaller than 0?
Null is not a value. That means that your variable has no numerical
so it
value.
Will, return false.
Yeah, if we don't assign it, so I'm removing this line, we cannot compare those. Oh, sorry, I commented out the wrong line. Yeah, the comparison here is false. Anything? Anything? So that's about it for the presentation for values and types and data types and variables. So we'll have time now for exercises. If you have any questions, now is the time to ask them. And if not, you'll have time now to work on implementation of the exercises, and I'll be here to help with that. All right, no questions?